Hi everyone, welcome back. Good morning. Hope you guys are doing good. Thanks for being here on Wednesday, December the 9th. This is our last regular class meeting. So after today, we're just going to be ready to take the midterm, or sorry, I should say final exam next week. But we have one more review session installment today to go over some more of the topics from the study guide and the class. So that's the basic plan. And I hope you guys are all doing well. Hi, Nathaniel. Good to see you. Okay, just a couple minutes, basically, and we'll be ready to roll. Hi, Rachel, Ruby, Melanie. Good to see all you guys. Hey, John, Valeria, good to see you guys. Okay, just another minute pretty much. Hey, Leo. Hi, Marissa. Hope you guys are doing good. Okay. So it's more or less class time, 11:30. So let me just get us started. Thanks again, everyone, for all your hard work throughout the semester and sticking with it through a tough year and obviously a tricky set of circumstances. But anyways, you've come to the end, so you've really made it this far. So congratulations for that. And all we have to now worry about is our final exam. I'm still grading the fourth homework that you guys just submitted the other day. Those will be ready over the weekend, and I'll notify everybody about that they can check for their scores. But yeah, basically, let's continue going through this study guide. We got through most of the first half last time, so we'll try to make sure to cover as much as we can with the rest of it today. As I've done in many cases before, I'm just going to pull up a Zoom meeting so that we can all look at the shared screen, and that'll help us with our review. So here I'm going to just place the link for that Zoom meeting here in the chat. Go ahead, use that, and as before, I'm going to keep this camera rolling so that you can come back to the YouTube channel and see the review session later if you do need to. Okay, so let's see you guys over on the Zoom. All right, good. See you guys here. Thanks. Let me get the shared screen going. Okay. So quickly, let's understand if we're all on the same page. Anybody maybe can type in some stuff in the chat here, and I can make sure you're hearing me. Okay, perfect. And you can see this the screen displaying the study guide here, right? Okay, good. So let's go ahead and continue where we left off. So we're in the middle of the truth table part of the review. I was showing you last time, or just reviewing with you, how to use a truth table to test whether a single sentence is logically true, logically false, or logically indeterminate. How to use a truth table to figure out whether or not a pair of sentences is equivalent or not. How to use a truth table to determine whether a set of sentences is consistent or not. And then there is using truth tables to see whether an argument's valid or not valid. So let's try and do that now. Suppose that you're looking at this argument which says, okay, if A then B, A, therefore B. If this is the argument and we want to create a truth table to see if it's valid or not, then as always, we start by making the cross, and then we list the premises to the left and the conclusion at the right in this top right portion. So we have if A, then B, A, and then over here B. Now, we have to place the downward arrow above the main connective, if there is one, in all of these three different sentences, which I hope is pretty easy to you guys to see. In this case, the main connective is the arrow because it's the only connective. And in the other two cases, there's no connective. It's just a single atomic sentence. So that eliminates all the guesswork about where to draw the arrow. Now here on the top left, we have to place the letters that are contained in the different propositions here, and that's just A and B. So A and B, how many rows do we need? Question for you. 4, right. So let's start with underneath A, T, T, F, F. Underneath B, T, F, T, F. So as we've always done, we have to simply match the truth value assignment given in each row to the corresponding value that's underneath the letter in that row. So top row, A and B are both true. Second row, A is true, B is false. Okay, third row, A is false, B is true. Fourth row, they're both false. Okay, now there's only one column that has to still be filled, and that's this one, underneath that arrow. So now I'm hoping you can just tell me what these 4 values should be. What are the T's, F's that occur starting at the top going down through this column? Someone will let me know. It's conditional, the arrow. So you'll have to understand when these arrow statements are false. Okay, good. Row 1, true. Row 2, you see it here, row 2. False. What about 3 and 4? Okay, good. The remaining 2, they're both true. We have 4 entries here. This is the only one that's false because to the left is T, to the right is F. That's the one and only combination of T's and F's for the arrow that leaves with the truth value of false. So TFTT. Okay, now, question, is this a valid argument or not? Who could tell me the answer? Valid or invalid? The table's complete, but now you have to look at it, examine it, and based on what you're seeing, you should be able to tell me it is valid. Yes, Lily. Why is it valid? Or how is it that you can see that it's valid? Let's make sure that everyone understands what you're using to give that correct answer. It's known as valid. It's seen to be valid because why? What is it that you're seeing that lets us all know that yes, it's valid? Anyone can say, but Lily can say too. What's the visual here that's telling you it's valid? So, Lily, you say when the premises are all true, so is the conclusion for each row. That's one way to put it. It's a bit awkwardly stated, though, I guess, because sometimes when an argument's valid, there's no case where the premises are all true. Like, there could be a case where in every situation, everything's false, and that would still be valid. So the best way to say it, Lily, is there is no row where what? There is no single horizontal row. No row of the truth table has what combination of truth values. There is no row where all the premises are true and the conclusion is false. One other minor correction, Lily, is that you say no TTF, but in some examples there will be more than 2 premises. So you have to be a little bit more precise. There's no row where every premise, however many, are true and the conclusion is false. So examine each row line by line. In the top row, we do not see 2 true premises and a false conclusion. It's everything true. In the second row, it's not that the premises are true and the conclusion is false. The conclusion is false, but also the first premise is too. So we don't have T, TF. In the third row, yet again, it's not T, TF. And also in the fourth row. So if there's no if there's no row that you can circle where every premise shows T and the conclusion shows F, that's the case of the argument being valid. Validity means there is an absence of any such row in which all premises are true and conclusion false. So that's a valid argument. Okay. Let's do another example of the same kind to make sure that we have good experience with doing these truth tables for arguments. Okay, so let's try this one. Premise 1, if A, then B. And then the second premise, not A, so therefore not B. Question, is this valid or not? Well, let's see. Truth table, we create it. We write the different premises in the order listed, and then the conclusion at end. Over here, top left, A, B. Just like before, that's 2 sentence letters, so it requires 4 rows. Okay, then arrows above the 3 main connectives. What are those? Well, it should be pretty clear because there's only one connective in each sentence, so it's the only possibility. Arrow, tilde, tilde. Okay, so now we're going to simply enter the truth value that corresponds to the assignment given in each row. We can do this one vertically, perhaps, to change it up. So underneath A going down, it's TTFF. Underneath B, TFTF. And same like here. Okay, so this column is going to be just as we had it in the other case because it's the same. So TFTT. All right. What are these for? Underneath that tilde to the left of A. Let me know. 4 truth values placed here in this space. Blank, 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 blank. What are those for? Okay, good, Tanya. FFTT. Because negation simply takes whatever the value is and reverses it. So FFTT. And last, this column. What's that one? Okay, good. FTFT. Okay, so question, is this argument valid or invalid? Valid or invalid? Now you just got to look at it, examine it, and give me the answer. Which case? Is it valid or is it invalid? Invalid, very good. Since it's invalid, which row is showing you that it's invalid? Row 3, that's the one that I would circle. So right here. TTF. This truth table has a row like that. It does have a row where all premises are true and conclusion is false. If there's any one row like this, which shows all the premises letter T and the conclusion at the far right, F, you circle that row, and that is the row which shows invalid. So when you complete a truth table for an argument, you have to like circle the 3 columns or however many there are above or underneath the main connectives, and then just examine it visually and look for a single row where premises are true and conclusion is false. You may find a row, and if you do, you'd circle it, and then it's invalid. If there's no row like that, then that's the case where the argument is valid, because in that situation, it's not possible for it to have all true premises and a false conclusion. Okay, now shortened truth table is the last topic mentioned on this first part of the study guide. You can use a shortened truth table to demonstrate that a sentence, a pair of sentences, a set of sentences, or an argument has a certain kind of status. So for an individual sentence, you can show that it's not logically false in a shortened table, which just gives the one row where it could possibly be true. If you have a pair of sentences, you can use a shortened table to show they're not equivalent, if they're not, by just displaying the one row where they don't share the same truth value. So you work backwards from the assumption that one is true and the other one is false. You can use a shortened table to show that a set of sentences is consistent by simply trying to create the one row of the truth table where all the statements are true and working backward from the assumption that they could all be true. And you can also use a shortened table to show that an argument is invalid by just creating the one row which displays that the premises are true and the conclusion is false. For example, in this one, suppose that the question was given in this way. Show me a shortened truth table that proves that this is an invalid argument. Okay, well, if this was a shortened truth table, then you're not going to create all 4 rows. You're just going to create one. Brenna, if on the final it asks for a shortened truth table, but we do it the normal long way, would it be considered wrong if we still get the right answer? No, I guess in that case, I would grant you credit, even though you're doing more work than is necessary in that case. One thing you could do, if that was happening, is create the full table, find out which row is the one that you need, and then erase it or create a second writing to the right of it, which just shows the one row. And then that would make clear that you understand that although you created the whole table to see where the row would be, you're then also able to simply create the one individual row. But it's not so hard to do it, really. Like in this case, suppose that we want a shortened table to show this is invalid. So we're working backwards from what assumption? That I should put what 3 letters down underneath these arrows? Tell me that. If this is a shortened table and we say it's going to prove that the argument is not valid, then what truth values will go here, here, and here? T, T, F. Okay, good. So let's do that. T, T, F. And so the logic just kind of helps you to finish. If this negation is true, that means that A is what? You see the letter T here underneath the tilde, but it's going to be the opposite of what's underneath A. So underneath A, the letter would be what? False, correct. So that tells us that A is false on this truth table. And then we simply, designate that value under A in the table and under each place where A occurs. Now B over here. Tilde B is false. So what's the value of B itself? True. So if B is true here, then it's true in all the other cases also. And now we've got our displayed individual row. And this FT row is the 3rd row of the truth table because, it's like this. It's this 3rd row, you see? But we only have to show the one row if the case is that it's invalid because one row proves that. Okay. So anyway, that's the shortened table method, just a little mention and reference to it. So now let's go ahead and take a quick look at our derivation rules. Let's go over the whole conjunction introduction idea. So suppose that, all right, you've got the following, so you're told to do this. Derive A and C. And you have these two assumptions, A and B, and you also have B and C. So help me get to this result. What would be your first inference in trying to, arrive at that conclusion? Here are 2 things that we are told are true, both A and B, and also both B and C. So what? You got to make an inference. So just tell me what to do. You don't have too many options when you really look at what kind of sentences these are. But yeah, you have to tell me what is the inference. So Jessica, you're saying conjunction eliminate from 1. Also same thing you're saying, Frida. Good. All right. You took A off of line 1. Line 1 says both A and B. That's a conjunction. When you have a conjunction, you can eliminate it. When you eliminate it, you remove one of the 2 elements, and then you simply cite the rule and then line that you eliminated. So we've got A, but this is our goal, A and C. So we got to wait until we get to that. Okay, so Jessica, now let's take C by conjunction elimination of 2. All right. And then what? Yes, Evelyn, you could have started with C and then done A. It's just your choice. As long as you get to the result at the end, sometimes there are more than one path to the same common outcome. Okay, good, Jessica. A and C. Conjunction Introduction 3, 4. I mean, this is like a real easy one, but you know, you have these two assumptions. You can see that A is on line 1. You can see that C is on line 2. So you can disassemble those two conjunctions with two successive uses of the conjunction elimination rule. That places the individual sentence letters here on line 3 and 4, and once they are separated from the conjunction, they can be added together on line 5. Okay? Is there anything there that is not clear? Everyone understands each step of this simple little illustration of the conjunction introduction / elimination rule, I hope. Okay. How about if A, then B and C. Okay, if A, then B and C. A, D. And you need to derive B and D. So what would you do to start this one? This is your goal over here. These are your 3 assumptions to start the proof. So what do you think? Just giving you an example. You need to make inferences to get to our solution. So we just got to get some kind of initial inference going. Okay, so good, Jessica. B and C from conditional elimination 1 and 2. Yes. All right. Line 1 says that if A, then this. Line 2 says A. So conditional elimination is when you have a conditional and then somewhere else you just have the part that's on the left of the arrow. When you have those two things, see how A matches this part that's on the left of the arrow? You can then use this rule of conditional elimination to get to the right-hand side of the arrow. So that's when you eliminate the conditional, the result is whatever the consequent is. That's why B and C is on line 4. We've used 1 and 2 to eliminate the conditional. Now we have B and C. But we're not quite done because obviously you see the goal is to get B and D. So what do you think is next? All right, Frida, Jessica, you're saying remove B by means of conjunction elimination 4. Yeah, so just notice, Frida, that it's line 4 that we are going to eliminate. So that gives B. Okay, so we're almost there, but we're not quite done. Now, Jessica, you're saying to reiterate D, but you don't really need to, actually. You can simply just use that numbered line to get the result that I think you want. Frida, you say B and D conjunction introduction 4, but there's just one problem with your justification. You have to give 2 numbers when you're doing conjunction introduction, because you have to cite the line where one of the parts is and also the line where the other thing is in the full conjunction. So let's get it right. Okay, Jessica, B and D, conjunction introduction 3 and 5. Mm-hmm. Okay, so in this proof, one of the steps involved conditional elimination. And so I'm just trying to make sure that that's something that we're clear about. Conditional elimination. You have a conditional, you have one statement somewhere else, which is equivalent to the antecedent. If you ever see that, eliminate the conditional. Cite this rule, use the 2 lines, eliminate the conditional, and get the consequent separated from the conditional. Now, Jessica, you say, would it be wrong if you reiterate D? It would not be wrong. It's a valid inference. It's just that it wouldn't be necessary, because if you had reiterated D, D would have appeared on line 6, and then I guess on line 7, with just one additional step, you could have combined them. But it would be an unnecessary step, because the existence of D on line 6 doesn't give you any more ability to conjunction introduce than just having it on line 3. So it would not be wrong, and it would not be deduction of any kind of credit, but it would just result in a less efficient proof because you'd have one more inference than is needed, but that's not a problem. As long as you get to the solution at the end and every inference is itself according to the rules, it doesn't matter how many steps it takes, even if it takes more steps than, let's say, the most efficient route to the proof itself. Okay? So far, so good. Okay, how about this? Let's say that we have these assumptions. If A or W, then C. Yeah, maybe I'll just go with that. And what I want you to derive here is that A and C. Okay, so these are two assumptions. What would you do here? What would be the method that you'd use to get this one going? Two assumptions. One is the letter A, the other is a condition. This is your goal, A and C. So what are we going to do? So Jessica, you're saying A or W assume? No, because conditional elimination does not involve any assumption at all. Conditional elimination, you don't say assume for conditional elimination. Conditional introduction is one where you make assumptions. Look here at the screen. You see these little stars? There's a star next to introduction for conditional introduction, biconditional introduction, negation introduction elimination, and disjunction elimination. Only those rows, only those rules can be used with an assumption to start the rule. All the other ones, you don't write assumption. You just give numbers and you do the rule itself. So conditional elimination doesn't have a star next to it. So you're not to say assumption, conditional elimination. Lily, though, good idea. You say disjunction introduction from line 1 to create A or W. Okay? Is everybody clear about this step here? Step 3, where did this come from? This is coming from line 1. Line 1 says A. Well, if we had A or W, then we could have a conditional elimination, which would give us C. How do we get A or W, though? Well, because with A up here, we can disjoin W to it. Disjunction introduction lets you add information to an already existing line. You add by introducing this wedge and then whatever you want to either the right or left. So we've created A or W. But we're not done until we get A and C. So what do you think is our next step? We have the ability now to make a new inference. Since we've placed line 3 in the derivation, line 3 enables us to make a new inference that we could not have made before that. So hopefully you will just see it. But let me know. What's the next rule that we'll use? Okay, good. C, from conditional, make sure to cite elimination, Frida. Arrow elimination, 2 and 3. All right, well, we're almost there. What is coming next? You can't stop until we get that. But we're right there. So what's next? Look at the proof, look at each line, consider what we need to derive, and tell me what inference we can use now. Okay, so good, Jessica. You're saying conjunction introduction 1 and 4 gives us A and C. And that's right. So in 5 steps, we arrived at our proof of A and C, given that A and if either A or W, then C. Okay, so clear enough here. There's a couple of other rules that now were used. Disjunction introduction, and another example of conditional elimination. In this case, conditional elimination happens because this is the antecedent of the conditional, A or W. And you can see that A or W sits on line 3. So those match. And that's why we can thus eliminate it and just get C. Okay, so let's continue then, trying to work with our different derivation rules. So there's also conditional introduction. So let's do that. Suppose that we've got A and B. Let's see. If A and B, then C. Or actually, here, I'll make it a little bit more interesting. So there's A, there's B, there's if A and B, then C. So I'm trying to think here. So maybe I want you to derive that if C, then B. Okay, so all right. What do you think? What do you think? We need if C, then B. You know, I don't know. This is not the best example in a weird way, but it's something that can be proven. And actually, I think it's a little too easy, but what would you do to get this one going? I kind of I put some unnecessary information there, but it won't problematize the proof. So you need if C, then B. What kind of sentence is that? What kind of sentence is if C, then B? Oh, well, Frida, I see what you're doing. You're saying A and B, introduce those by conjunction introduction. Okay, A and B, conjunction introduction 1 and 2. We need a conditional ultimately, but anyways, I'm just taking the steps as I see you writing them. So A and B, conjunction introduction 1 and 2. All right, then what? C, conditional elimination 3 and 4. Okay. But we're still not to what we need, which is if C, then B. So what do you think? I mean, you need a conditional, so think of the rule that will spit out a conditional. We're not to the end. The proof is steering for this. So what do you think? No, Jessica, what do you mean? When you write what you think we can state on the board, you have to give the rule. So if you're saying C then B, you'd have to tell me what rule. But right now you can't write that. Conditional introduction 2 and 5. No. You're losing the plot a little bit. Conditional introduction requires an assumption. Lily, you're saying, can we erase those steps and write C, assume for conditional introduction? Well, we don't need to erase the steps, though, Lily. I know that you're thinking, well, we don't need these steps. But none of them are incorrect inferences, so we could just leave them there. But you're right that we have to add the assumption of C for conditional introduction. Now, come on, everybody. What's up with conditional introduction? You have to be clear on this rule. I keep noticing that people have difficulty simply starting the rule. If you need a conditional, you have to assume the antecedent of the conditional. Then after that, you have to find the consequent, and it has to occur within the subderivation. So we're looking for what to place here? What do we need to occur inside of this subderivation if we're going to end with C arrow B? Question for anybody. Currently, what do we need to have written inside the subderivation? Yeah, we need the letter B. So we can reiterate it from 2. Okay, so we assumed C. We were able to establish B within the subderivation. So then what happens in line 8, I guess, here? Yeah, just let me know. On line 8, what shall I write? C arrow B, conditional introduction 6 of 7, correct. Now, the problem itself is not the ideal example because I gave you some information like line 1 and line 3 are not even necessary. You could have proven this just on the basis of B because you could have like assumed, say that was line 1, assumption B, prove this. Then your line 2 would have been assume C, and then you could just reiterate B, and basically 3 steps you'd be done. But anyway, that's the case here. Let's do another one of these conditional introductions because I think it's something that you must have a little practice with. So suppose that I need you to derive the following. Derive that if B then either A or B and C. Well, actually, hold on. Okay. So if B, then either A or D and C. And here are your assumptions. A and C. Okay. Now tell me, what statement do you have to derive? What kind of statement do you have to derive here in this case? The goal sentence that will appear on the last line of the proof is called a what? Yeah, just what type of sentence is this? So there's 5 types. Okay, good. It's conditional. It's a if then. So we want a conditional. What rule is often used to establish a conditional? What rule can be used to prove or to show a conditional? The rules won't change. I mean, these rules stay the same. So, I mean, once you understand it, it's something automatic. You need a conditional, so you're supposed to use what rule? Conditional introduction, correct. So, do it. What is the inference on line 3? Okay, let's assume B for conditional introduction. Now, what's the goal now inside of the subderivation? It's to build this thing, which is a conjunction. And the conjunction has one element, A or D, and on the right, the other element is C. So we need to somehow find A or D and C inside of that subderivation. So continue. What's your next inference as we try to work towards this? Number 4, the fourth inference, or the fourth step in the proof. So we got as far as the assumption of B, but you got to continue and work through the remaining steps. So there's, 11 rules. There's 3 sentences here. So you got to make use of those rules together with these sentences to get the goal that you're looking for. And the goal you're looking for is that either A or D and C. Well, that both either A or D and also C. So go ahead, tell me next inference. What's that? A or D, disjunction introduction of 1. Yes. Line 1 says A. You should look at that. You should see that it says A and that A is something within this consequent. Sorry. So we are able to add to the A the letter D with disjunction introduction. When you need a disjunction of whatever kind, and you have one of the 2 disjuncts, You can freely add the other one with disjunction introduction. So we have A or D, and that's great. But we won't finish the proof until we have this conditional specifically. So we got to continue. What's next? Drawn red, good. But one thing is this. You have to give two numbers. You can't just say 4. If you're doing conjunction introduction, it has to be 4, comma, wherever the other thing comes from. So almost. What would you like to correct on that? Yeah, 2, 4. Okay, very good. So A or D and C, and that is conjunction introduction to 4. So look at this. This is the information that's inside of our subderivation that started with B. From B, we were able to provide this in the subderivation. And so now you should be able to tell me how we close this out. What is line 6 specifically? Line 6 of the proof. You know, we're at the end, so. Okay, Andre, very good. B, arrow, and then the complex expression. The only one thing you don't have, Andre, is a right parenthesis that goes after the letter D. But other than that, yeah, you're right. So B, then either A or D and C. And that is conditional introduction 3 through 5. Okay, so that's the proof of this one. And this is just another look at conditional introduction, disjunction introduction, conjunction introduction. Okay, so let's try some of the biconditional introduction stuff. Okay. So maybe let's say if A then B, if B then C, if C then D. Okay, so then if I assume A, B, B, back to A. Let me change it up. Sorry, I don't want that one. I think I could get a better example maybe in the book. So let me think about giving that case. Okay, let's do this one. A little bit more work. Derive D, double arrow, not B, and starting off with these 3. Number 1, if both A and not B, then C. Number 2, if either C or D, then in that case, D if and only if not B. And then the third, both not B and A. Okay, so in this case, there's no glare. Okay, good. So in this case, what kind of sentence is it that we need to prove? So new proof, new question. What kind of sentence is this, the goal? So there's 5 kinds of sentences. There's conjunctions, disjunctions, conditionals, biconditionals, and negations. This is a biconditional. The double arrow is biconditional. So what rule is often used to establish a biconditional? Remember, there are rules with the names of each connective. One to create such a statement, and one to eliminate such a statement. We're trying to build a biconditional. Therefore, the rule to use is called what? Just need to give me the name of the rule. It's just scratching the surface. I mean, it's much more complex than just saying, okay, you need to do biconditional introduction. You need to know the rule, then you have to actually apply it. So biconditional introduction, correct. How do we start if this is our biconditional that we want? How do we start this proof? By doing what? Or I don't know. I mean, you know what? Actually, this is not going to be biconditional introduction. I'm sorry, guys. My mistake. But I mean, in a way, it's maybe possible to get to that same kind of result. I'm looking at a problem in the proof set of our textbook. This is actually more biconditional elimination because look at how this is the consequent here. This statement is the same as the statement above. So we'll get to biconditional introduction, but let's just solve this problem really fast. We want to get to this antecedent because whenever we get this, then we can eliminate line 2 using conditional elimination, and we'll simply have this as our final result, which is what we want. So we want to find somehow C or D. C or D. How can we get to C or D? Well, one way we could do it is if we just had the letter C, and then we could use disjunction introduction. So we're like reasoning backwards here. Let's eliminate A. Very good, Andre. So conjunction elimination will give us this letter A. Conjunction elimination, line 3. Now we have A on line 4. Since we have A, what's next step? Andre, I think if you knew to do this, then you're probably already wise to the next step. Okay, good. So B. That's another case of conjunction elimination of line 3. Sorry, not B. It's B. Be precise. It's what? Tilde B. Thanks. Okay, so tilde B is line 6. A is line 5. Take a look at line 1 and 4 and 5. Now I'm giving you a big hint. What do you think we should do so that we can create this information and eliminate the conditional? We need the antecedent from line 1 to exist. And we have all the parts. Good, Frida. Just give me the rule and the lines, please. So you've got it. Yes, conjunction introduction 4 and 5. So that's A and tilde B. Okay, so there's A and tilde B on line 6. Now we should see line 1 and 6 and think about what the next step could be. What is that? Yes, help me with that next step. Okay, so C, conditional elimination, 1, 6. Very good. So what? We have C. How's that going to help us? Having established C, we're a couple steps away from getting here. Because look at line 2. C is one of the parts of this disjunction. So since we have the left part of the disjunction, how can we possibly then get to the full disjunction that we want so we can eliminate the conditional here? What's the next move? Okay, good. Again, thanks, Andre and Arlene. You see it as well. Good, Jessica. C or D. C or D on line 8 follows from disjunction introduction of 7. From 7, we can disjoin anything. And so let's do D. That gives us the antecedent that we're looking for. So line 9, we've come close now to the very end. What is line 9? Take a quick look at line 2 and line 8. And then let me know what you think is line 9. What is it? It's right there. You're looking right at it. Line 2, line 8. Okay, good. Andre, D, if and only if not B. From 2, 8, conditional elimination. Okay, so yet another proof. Now let me go back into some of the subderivation stuff. And we've done conditional introduction subderivation. Let's try and do a biconditional introduction. So now for real, biconditional introduction. derive this. H, if and only if, just in case, J. And two assumptions provided are these. H and I, if and only if J. And also H, if and only if I. Okay, so now, legitimately, we do have to use the rule of biconditional introduction. This biconditional is what we're trying to build up. So to get it started, how do we start biconditional introduction? That's the next question for you. Line 3, I'll tell you, it's going to be biconditional introduction. That'll be the rule. But what is the assumption made to start this? Okay, good. Let's assume H for double arrow introduction. Why did we do that? Well, it's because H is the left side of this double arrow. So the way it works is you assume that left side, whatever it is, in this case it's H, and then in the subderivation you have to ultimately get to the letter on the other side or the formula on the other side. So now we're on the hunt for J. When we get from H to J, that stops the first part of the biconditional introduction, and then we have to run back from the other side. So when we get from H to J, we'll make an assumption of J, and then we have to somehow reach 8 things, then we're done and we write the biconditional. So anyway, we're on line 4 now, and remember, here's our current goal, J. So what do you think could be our next step to advance this proof to this fourth stage? H is there on line 3. So with the addition of each new inference, you have to think about maybe how that is the next step, right? Since you've got H, you should use it. So Jessica, you say H and I, but you can't, no, you can't create H and I because there's no, the letter I does not appear on a particular line, I mean by itself. Arlene, you say biconditional elimination 2 and 3. Very good, yes. So that gives us I. Biconditional elimination 2, 3. So remember, biconditional elimination is the same as conditional elimination with the one extra thing that you can also go from right to left. So here we have H, double arrow, I. Line 3 says H. Those two things match. And that's when you can eliminate the biconditional and get the other side, namely I. So line 3 says H. Line 4 says I. We're still ultimately trying to get to J. So what's next? Having placed I on line 4 gives us more inferences that we can now make. But just take a quick look at all the steps there and just think of what is our next logical inference. Okay, so yes, good, Arlene. It's H and I, which is the basis of conjunction introduction of 3 and 4. So we made another inference. Very good. We're getting close to this goal of J, but maybe you can tell me what's the next step. Okay, good, Andre. Yes, J is on line 6, and it's based on biconditional elimination from 1 and 5. The reason that we created 5, H and I, is so that we can eliminate this biconditional and get to our goal, which is J. So H led to J, very good. But that's just part 1. Now on line 7, we have part 2 of this biconditional introduction. And what is the assumption that is going to be made on line 7, according to the rule of biconditional introduction? Okay, correct. Good, Andre. H was the first assumption, and we got from there to J. Now part 2 is assume the other side, opposite side, and get from there back to H. So we're assuming J for biconditional introduction. All right. So what do you think? got to get back to the letter H. So what do you say? Okay, very good, Lily, yes. H and I, same Jessica. H and I follows now from the combination of 7 and 1, biconditional elimination from right to left. Okay, so we just used J, which was assumed for introduction here, to eliminate this first biconditional. Now we have H and I. Keep in mind the goal here is going to be H. So line 9. How do you think we're going to get to our goal of H? Very good, Andre. Yes, it's just conjunction elimination from A. So finally then, we arrive at line 10. H led to J. The assumption of J led to H. So if we understand how biconditional introduction works, we should know then what to enter on line 10. Because the procedure is basically done. When you get from one side to the right, and then from the right side back to the left, you've proven your biconditional. So just the right way of closing the subderivation. Okay, good, Andre. It's going to say H double arrow J based on biconditional introduction, and then you've got the right numbering. 3 through 6, 7 through 9. Okay, in 10 steps, then we have our proof of H, if and only if J. So one more example, this one making use of biconditional introduction. So sometimes you have to build a biconditional using this rule, and there's part 1 and part 2 for every case of biconditional introduction. Part 1 is the assumption of the left side proceeding to prove within the subderivation the thing on the right. Part 2 of biconditional introduction is the reverse, assuming the opposite side and through inferences arriving at the other, other side of the biconditional symbol. H to J, J to H, done. H double arrow J. Okay, so that's the biconditional intro. So then, okay, let's do some negation stuff. Let me see what I want to use for this. Okay. Just trying to find like a nice solid example here. Maybe how about this? Okay, let's see where we're at. Okay, this one's pretty easy. So let's try this one. I'm cutting off some of the answer material, but this is the problem looking at D. So here's the case. We need to derive not M. And we've got two primary assumptions. Number 1, M just in case T. And number 2, that not T. Okay. So what we want ultimately here is this negation of M. So now I'm trying to help you think about the negation rules. When you're trying to build a negation, the rule that is often used is called what, and how would it work? Tell me then if you think you know. What is line 3? And what kind of inference rule are we going to use? We need tilde symbol M. Very good, Jessica. So we can assume regular M for negation introduction. We want to add a tilde to the assumption that we're making of M. That's negation intro. So here's the subderivation. M is the assumption assumed for tilde introduction. Now, question. These negation rules, how do they function? What do you have to find inside the subderivation to close it? When you start off the subderivation and it says negation, either intro or elimination, that's right, Arlene, you need a contradiction. So you need a pair of two statements where one has a tilde to the left and then the other one is unnegated. So yeah, let's try to get our contradiction. It's not so hard, actually. What do you think would be the next inference based on the rules that we all know? Okay, Andre, very good. T, and same to you, Arlene. T, where's that coming from? It's coming from biconditional elimination because number 1 says M double arrow T. Line 3 just says M. Those two things combine to eliminate the biconditional and give you T. So that's biconditional elimination 1, 3. Remember though, we need a contradiction. Where will it come from, you assume? Okay, very good, yes. Reiterating line 2, which is the negation of T. So on line 6, we're ready to close the subderivation, but what will be the outcome? What's the output from this subderivation? It's spitting something out. After we find a contradiction, what's generated by that is the reverse of this. So it's tilde M. And that is based on negation introduction, line 3 through 5. Okay, so just an elementary example here involving negation introduction in this case. Okay, let's see. Maybe there's a negation elimination case that I can also quickly refer us to. Sorry, let me kind of move this to the side for a bit.
So there are pieces of which make sense. Yeah, but for the most part, you have a general sense. So there's reasons to use it. Why don't we discuss masculine as its own issues, right? So one big issue.
Okay. Let's see, is this one kind of crazy? That's tough. This one's tough because the contradiction here is a very complex contradiction. So I feel like if I give you that one, it might be a bit confusing. Okay. It's another case that's kind of like that. I'm just scrolling. Okay, I think this one's not quite so bad. Let's see if we can do that. So it's going to start with, you need to get A. And once you have A, you'll have A or B. Okay, all right. A little bit crazy, but let's try it anyway. So in this case, you need to derive, you need to derive B. And here are two assumptions to start. Number 1, A and B if and only if A or B. That's an assumption. And then the second assumption, is that, oh, am I looking at this part above? Yeah. C and C if and only if tilde tilde A. Okay, so just to give you the helpful hint about how we're starting this, because it's not immediately obvious. The first thing we're going to try to do is to do negation elimination for tilde A. If we finish that subderivation and we end up getting just A, then we can do disjunction introduction, and then that'll allow us to eliminate the biconditional. And then from there, we can just detach B from the left side. So we're really kind of on the hunt for A or B, and that means that we would like to maybe find A, the left component. So let's assume tilde A, and that's for negation elimination this time. We're going to try and strip that tilde off. Okay, so there's tilde A. So next up, what do you think? What do you think? Is there an inference here that we can make that you're able to see? I don't want to give away too much, but there's definitely one thing that can be done now in terms of line 4. Look how line 2 is a conjunction. Whenever you see a conjunction, always consider eliminating it, because sometimes having one of the two sides of it by themselves is very useful in going further in a proof. So I'm giving you some hints. They kind of have something to do with line 2. But go ahead, tell me. Okay, good. So Frida, Lily, you're saying take C away from line 2. Conjunction elimination 2. All right. Well, let's go all the way and do that again to get the other part. So if you know what I'm saying, what inference am I kind of suggesting on line 5? Because, right, every conjunction can be eliminated twice. You can take one part off in one inference, and you can take the other part off in a subsequent second inference. So we took C, but there's two sides to every conjunction. So what do you think? I'm suggesting to do what? Good, Lily. So let's remove the other side, which is this biconditional statement. See, the main connective here is and. C is the left conjunct. The right conjunct is the whole formula in brackets. So we have now C double arrow, tilde tilde A. That's also conjunction elimination of 2. Okay, so I don't want to give you too much a hint right now because I'm hoping this is kind of coming clear to you. Just look at this and tell me what you think is the next inference. And always take a good look at the most recent lines, because often those are the ones that are of use to create the next inference. Okay? So we need something on line 6, and there's certainly an inference right now that's available that we have not yet made, and it proceeds from the new stuff on line 4 and 5. Okay, Jessica, you say tilde tilde A, biconditional elimination 4, 5. That's correct. Okay, so don't forget, this here is a negation subderivation. So what we have to have inside is a contradiction. And we're actually very close. Good, Lily. Let's reiterate line 3. Then it will sit right here. And what it says is tilde A. But notice, what is the negation of tilde A? It's this, tilde tilde A. So these two are opposites. This says it's not the case that not A. And this says not A. So those both cannot be true. They're contradictory. So in other words, what's written on line 8? What's written on line 8? Since we found our contradiction as we needed to find it. Good, Andre. That means that we simply can now write the opposite of tilde A. We eliminate the tilde, and it's just saying A. Negation elimination, and the lines are 3 through 7. So now we have A, and it's sitting on line 8. What do you think we can do? Because we're still ultimately steering towards B, and we don't have it quite yet. Okay, good, Lily. A or B. Disjunction introduction on line 8 gives us A or B. So now with A or B on line 9, look above. Tell me, what can A or B allow us to do? Because I know that we create A or B here, but not for no reason. We do it for a particular reason in order to create another inference. So A or B gives us the power to now write A and B. Biconditional elimination 1, 9. Right. So finally, we've got to the end. That's line 11. What do you say is our 11th inference to finish the proof? It's just B. Good, Andre. And it's conjunction elimination of 10. So there you go. In 11 steps, we got to the proof that we needed. And we passed through a use of negation elimination along the way. So now we've got a little clarity on that. And you see the same steps written here in the solution in the answer guide. Okay, so let me now try and do a little disjunction elimination with you. So let me go up here and see what's a good example to go off of.
Comparing using skills, argumentation, skills of rationality, judge whether
Okay, just gonna try and get a good example. I think I got a little bit further down, or actually maybe above. Because I just noticed one here out of the corner of my eye. Okay, a little complex. Let me swing down a bit further below. That one's pretty complicated for sure. This is the section I'm trying to find though. Okay, yeah, so see. Okay, yeah, let's go ahead and do this one. We'll just work through this one real quick. So I'm looking at letter H on the bottom. It says derive A. And 3 premises are stated, and they're these 3. First of all, if not B, then A. And then either C or not B. And then finally, third, not C. So, okay, here we need to get A. And these are our 3 assumptions. So let me just tell you, so that we can make sure to get through it, that we're going to begin with disjunction elimination. Essentially, if we can somehow prove tilde B from both of these disjuncts, okay, hear me? If we can prove tilde B from both of those 2 disjuncts, then that will show tilde B by itself. And then when that is all complete, we can eliminate the conditional and we'll be done with the proof. So let's try to get both sides of this disjunction to lead us logically to tilde B. Therefore, we assume first C for disjunction elimination. Now, disjunction elimination requires that there's already a disjunction somewhere above. You begin by assuming the left side of it. In this case, that's the letter C. That's why we assume it for disjunction elimination of 2. And now we're off and working towards our real goal, which is tilde B inside of here. So if tilde B is the goal, the sub-goal within this sub-derivation, what kind of rule sometimes allows us to build up a tilde statement? Tilde B is the new goal, because we want to find it from both of these 2 sides. If I want tilde B to be my ultimate outcome, what rule can sometimes be used to supply or generate a negation? It's called, negation introduction. So if I'm going to do negation introduction to get tilde B, I have to make my new subderivation here with what assumption to start? Tilde B is what I want as the output. So with these negation rules, you have to start with the assumption of the opposite of what you actually want in the end. Since tilde B is desired, and negation intro is our rule, we will assume what on line 5? Good, assume B. And since it's a new subderivation, we have to indent. So that's B, assumed for negation intro. Now here in this subderivation, what is needed is a contradiction. And actually, it's not too hard to get that contradiction, but you should tell me where I will find it, where will I get the 2 things that contradict. So just help me with line 6 and line 7. Contradictory things should appear there. Okay, Frida, C, reiterating 4. And then line 7, I need the opposite of that. And very good, that's on line 3 already. So that's tilde C, reiteration of 3. So then here we go. B was assumed for negation intro, and there's a contradiction right away. So that means we can close this. And the result outside of this scope line on line 8 is going to say what? Line 8 will now show what statement? Line 8? Just following the rule, we assumed B, negation intro. We wanted contradiction, boom, we found it. So we close it, and that says not B, correct. From negation introduction, 5 through 7. Okay, so here's tilde b. And what was the goal starting with C? To get to tilde b. So done. But now we have to do, 9. Now we have to do the second part of disjunction elimination. So who can tell me what assumption has to begin here on line 9? Since we're not finished with disjunction elimination yet. We've only done the first half. So the second half starts with assuming what thing? That's right, tilde b, the other side. Now, let's all be very clear about this. When you do disjunction elimination, you need to get to the same thing from both sides. So from C, we got to tilde b. That means that now that we've assumed the other disjunct, we have to get back to the same result. But it's very easy when tilde b is the disjunct itself. So what is line 10? We need to get to the same result as before. So right, it's just reiterating line 9, tilde b. Reiterate 9. Okay, so I guess I need 2 more lines, or maybe 3. Line 11 then is just where we say tilde b. Tilde b now is the result of disjunction elimination 2, 4 through 8, 9 through 10. Sorry, 4 through 8, 9 through 10, tilde b. So I know it's kind of low on the board, but now that we have tilde b, what would be line 12 of the proof? A, yes. And that's resulting from conditional elimination 1 and 11. So A was proven, which was the goal in the series of 12 steps here. So this one required a little disjunction elimination. We had to break down line 2 so that we could get tilde b from either side of the disjunction. Doing that gave us the ability to eliminate our conditional, and that releases A, which is the ultimate objective. Okay, guys, so we've covered all the derivation rules. Let me see what you're asking, Frida. Do you need to do the closing for the subderivation? Yes, but I did here on line, no, I did, yeah, line 11. Line 11 cites that tilde b was the common result of 4 through 8, 9 through 10, and initially based on this disjunction line 2. Yeah, sorry, so it was a little small, but that's shown on line 11 if you can see it. And here, I'll make sure it's present in the proof on the board, or sorry, in the shared screen. Take a quick look and you'll see. Just clearly and legibly shown right here. This is the problem that we just did, 11 steps, and they're all exactly the same as shown here. Or wait, no, am I wrong? C tilde A, C not C A. Okay, they actually did it slightly differently, which is interesting. They made A be the common result of the 2 subderivations, but actually saved them 1 step. So here again, I guess you can see a case study in how like a different series of inferences can also lead us to the same result. The only difference in this case is that the author decided to make A be the common result of both. Had I noticed that when assuming tilde b, we could just use it to eliminate and get A, then I would have probably thought, okay, let's make A be our goal inside of this negation subderivation. But I guess I have 1 additional step, less efficient, but not to worry. Okay, guys, so thanks so much. It's been great working with you guys all semester on logic. I'll be in touch over the weekend as I finish up grading these last homeworks that you did. I'm still going to try and award certain kind of extra credit, but I had a busy day yesterday with grading and teaching, so I just want to give myself another day to send the announcement through to everybody, but I'll certainly do it before the weekend, so not to worry. Other than that, good luck on all your other finals and tests. And it's been really great teaching you guys and passing along, some of this knowledge that we've all inherited over the last thousands of years. There are evaluations that are given for student evaluations for their professors. I believe the window is open for that. So I would just encourage you guys, if you do have time, I'd appreciate it. Do we need to be on Zoom for the final? No, Brenna. You'll be on your own. I'll send you the test form at the appointed time. But I won't be monitoring you or proctoring you like in a Zoom. I just think that makes it more complicated. And so yeah, no, not to worry about that. Yeah, but thanks a lot, guys. You know, I really love teaching. I really care a lot about my students. Logic is a tough subject. There's nothing really I can do about that. It's you know, famously something that everyone struggles a little with. But I'm just trying to make it as accessible and relatable to you as I can, even though it's definitely abstract. And in the end, we're going to have, you know, a fair curve, and I'm going to make sure that there's a normal distribution of grades. But you still want to reach for your highest score possible to ensure that you can get the best grade possible for yourself. So anyways, thanks again. I don't want to take more of your time today, but have a great afternoon, and we'll definitely be in touch. So thanks, and take it easy. Bye-bye. So Zoom meeting's ending. And then to the YouTubers that are still here, hi guys, see you next time, and have a great day. Okay, bye-bye.